Okay, we want to get the x-intercepts and long-run behaviors of each of these functions, okay, each of these polynomials. So the intercepts. Now, I really recommend that you write out things the way I'm writing them out. Okay, if you write out the words that I'm writing or words to the same effect, you're going to retain the information and be able to use it if you encounter something a little bit unfamiliar. So let's start with this one. We have 2x minus 4 multiplied by 3x plus 5 multiplied by x squared plus 4 equals 0. Now there's some words you could write before that. 0 is a curve when y equals 0, right? X-intercepts. When y equals 0. If every time you work one of these problems, you write this out, then you'll know to write this equation, because that's what you get if you let y equal 0. Okay. Then you have to realize that this splits into 3 equations. So we get this equation, this equation, this equation. And that's by the 0th property of multiplication. Myself and next to write the words. By the 0th property of multiplication, this is equivalent to this or this or this. That's a logic that you want to understand, because it makes you better at understanding the logic of mathematical reasoning. And more to the point, if you want to do well on tests and so forth, it reinforces what you're doing and why you're doing, so you can be sure that you know you're doing the right thing. Okay, so now we have 3 equations. We solve each equation. So I'm going to just jot down the solution, which you can certainly do yourself. Now you can pretty much just see what the solution to the equation is, but I would write down a couple of steps just to remind yourself that there are steps to be taken to solve an equation. Okay. Okay. So you get x equals negative 5/3. X squared plus 4 equals 0. So a little more to this. You subtract 4 from both sides, you get x squared equals negative 4. Solution to x squared equals whatever is x equals plus or minus the square root of whatever. And the square root of negative 4 is not real. There's no number that can multiply by itself to get negative 4. Okay. And if you're a little unsure about that, you should be writing that out too. It takes a little longer to do a problem if you write out the logic and so forth. But if you look at the way I'm writing these out, you can see the logic. Okay. And I think open math tells you the logic. They often will skip steps. They'll say, okay, here's the equation, here's the solution, because they assume you already know how to solve that equation, which you do. But did you actually take the trouble to solve the equation, or did you just write down 4 is a root, -5 is a root, and -4 is a root? Because that's what you're used to seeing, okay? You're bypassing the process of setting up the problem and actually solving it. And when you get something like this, you know, everything so far has just been x plus 5 and x minus 4, you know, so forth, okay? Not a whole lot of x squared plus anything. And if you're in the habit of just taking this number, this number, and this number and changing the sign, it lets you down. Okay, you don't get the solution. All right. Then we can use the same logic here. Now you ought to write down x-intercept when y equals 0. Every time you write that down, it sinks in a little better because it's really important. And people throughout a pre-calculus class will typically confuse it. Okay, typically won't take that step in solving the problem. Okay, so anyhow, we have x minus 3. And yeah, we should write this out. X-intercept when y equals 0. There, I wrote it out. You can't prove it. You can't prove that I didn't. But yeah, I really didn't. Okay, but that just indicates you ought to write that out. X squared minus 5x plus 6 equals 0. And another benefit to doing this is if you make a mistake in the algebra or do something and you've set it up like this, I'm going to give you a lot more partial credit than I would if you just write down the wrong answer. If you just write down, well, that's 4, that's -5, that's -4. Totally wrong. It doesn't give you 0. You can plug those numbers in and they will not give you 0. Okay. Another thing is you really should be checking these. At least check a few of them. So you know what it means to have a solution. Okay. So here we have anyhow this. Zero cooperative multiplication. We get x minus 3 equals 0, or x squared minus 5x plus 6 equals 0. Well, you run through the solutions. Clearly by inspection, x is going to be 3. Now, you can factor this. It's easy to factor x minus 3 times x minus 2. X minus 2. It's easy to factor this, but a lot of times it's not going to be factorable. In other words, typically, if it's a real world situation, that's not going to be factorable. Real world doesn't give you nice factorable quadratics very often. Okay? But sometimes it gives you something that's close to a factorable quadratic. So you say, well, it's going to be close to this. That can be helpful. Okay, so there are times when you do need to be able to factor, like if a test asks you to factor something. Okay, anyhow, you get fill in the quadratic formula, you get 5 halves plus or minus the square root of, well, 4ac is 4b squared is 25, so that'd be square root of 49 over 2. And square root of 49 is 7, that's 7 halves. This equals 6 and equals 6. What's going on? Uh-oh. My minus 4ac was 1, it'd be 25 minus 24, not 25 plus 24. So now 5 halves and 1 half is 6 halves, which is 3. 5 halves minus 1 half is 4 halves, which is 2. Okay, so my zeros are 3, 3, 2. Okay. They have a solution set of 3, multiplicity 2, and 2. This is how you find the zeros. And again, I urge you to write out the details. And we don't end up stuck with something that you don't really need to be stuck with. Okay. Now, let's graph. Okay. Your x-intercepts are at 2, -5/3, and that's it. Oh. Yeah, okay, so 2, I'll just put 2 here. X equals 2, so you have an intercept here. -5/3 is -1 2/3. It's almost -2. So it's going to be just a little closer to the y-axis than this. It's going to be negative. And we have an x-intercept here. Now I haven't figured out the y-intercept. But the y-intercept you can write it out, all the multiplications by 0. That equals -4 times 5 times 4, which is -80. So let's go ahead and draw a line for y equals -80 and locate our y-intercept here. Now, long run, the degrees 4, the expanded form, you're going to have a 2x times a 3x times an x squared. That gives you a 6x to the 4th. Then you got a bunch of stuff in the middle. And at the end, you got -4 times 5 times 4, which is -8. So this is like it's like 6x to the 4th. What's x to the 4th? Well, if you understand the graphs of power functions, it's kind of like this. Kind of looks like a parabola, except it's flatter through the middle and steeper on the edges. We have been over that, but that's the way it is. And I'm not sure we've been over that in this class, but that's the way it is. Now, the way open math tells you, just plug in some big numbers. Understand that if x is really big, all these are really big, and they're all positive. if you multiply four really big positive things together, you get a humongous positive thing, which tells you that the graph goes up like this. Understanding this also tells you that the graph goes up like this. And this is a better picture. As I've said before, I'm not sure in here, what you essentially have is, this is like this, but it's got some wiggles in the middle. Possibly, okay? Turns out it really doesn't, or there are probably wiggles, but you don't know how to find them. But there could be wiggles in the middle, and usually are. In this case, we got to go through these 3 points, and it looks like this. And if x is a big negative number, this is negative, this is negative, this is positive, because the square of any negative number is positive. So you got two negative big numbers and a positive big number, which gives you a positive big number. So your y values go up like that. So now our graph, the best you can really draw it is it's almost symmetric and it almost looks like a parabola, but our best guess is it's pretty flat here and then pretty steep here. So it's not a very interesting graph. There might be some wiggles in here, okay, because of the x squared plus 4. But we're not going to analyze that. You learn to analyze that when you take a calculus course, because you got to use derivatives, stuff like that. Okay. Now, I'm not going to take the time to write out all the details for this one, but what's the degree? The degree is 3. We found the x-intercepts. The y-intercept is what you get when you let x equals 0. It's 0, negative 18. Now our x-intercepts are 3 and 2. We've got to go through the x-axis here and here. We go through the y-axis at negative 18. I'll just put y equals negative 18 here. And degree 3 implies that the long run looks like a cubic function. Meaning, you start down here, you end up here. You go up to negative infinity on this side, positive infinity on this side. So we're going to come up from negative infinity, maybe about here. And now we've got to go through these 2 points. Now, if I come up here and go through this point, turn around and go through this point, I'm never going to get back up here because I can only go through the x-axis when the polynomial is 0. And there's no number other than negative, other than 3 or 2 that makes it 0. Any other number isn't going to give you 0 here. This has got to be 3 in order to be 0. Any other number here, other than 3 or 2, isn't going to give you 0. Okay? So you have 2 numbers that aren't, or 2 numbers that aren't 0. They're supposed to be 0. It just can't happen. Okay. Now the problem is, of course, if we come up above this point, or if we come up through this point and turn around and go through this point, we can't get up here. Well, here's where you got to realize that really you've got 3 zeros, but one of them occurs twice. The one at x equals 3 occurs twice. So that means we come up here. We come down here, and this is a 0 of degree 2. So it acts like a squared function close to this point. So there it is. Now we've been over most of that. But this will give you a synopsis. Okay. Okay. Okay, coming back to this polynomial, the first one here. Our zeros that we got by solving the equations, writing out all the details of the logic and everything, so we remember it, are x equals 2, x equals -5/3, and x equals plus or minus the square root of -4. Now, what do we do with the -4? -4 is 4 times -1. And square roots work like this. The square root of a product of two numbers is the product of the square root. So we can write this square root of -4 as 4 times the square root of -1. Of course, the square root of 4 is 2, and the square root of -1 is I for imaginary. It's not a real number, it's an imaginary number. Now, it turns out that imaginary numbers really are real if you go a little deeper into reality. But you'd have to pretty much have an undergraduate degree in physics to understand that. Okay? It gets into quantum mechanics in a pretty deep way and a huge amount of mathematics. Most engineers don't get that far, but some do, depending on their field and how deep they want to go into it. But I can get an undergraduate degree in mathematics without ever really understanding the reality of I, the deeper reality. Okay, so we call it imaginary. And we call these the zeros. This doesn't give you an x-intercept because we're only in what we call the real numbers when we're graphing the thing. And this is not a real number, except in a deeper reality, okay? And something you really need to understand. It doesn't give you any zeros. It doesn't give you any x-intercepts. Zeros then are 2, -5/3, plus 4i, and -4i. Okay? Now, and let's go ahead and call this P of x. This means that Px is a multiple of x plus 2 times x minus 5/3 times x plus 4i times x minus 4i. Now, what's the multiple? Well, if we expand this, as we saw a minute ago, we're going to get a 2x times 3x times x squared, which is 6x to the 4th. If we multiply these out, we only get x to the 4th. We don't get 6x to the 4th. But it's a multiple of this, and that multiple's got to be 6, so that gives us the right x to the 4th term. Okay? There are other ways to see this, but that's a straightforward way of reasoning it out. Now, you might be tempted to just throw the 6 under one of these x's. But if you did, that would change the 0. If you have 6x plus 2, you would no longer have a 0. Uh-oh. You know, I did something really there. You have to have a 0 at 2, so you have to have x minus 2 as a factor. Okay? At x plus 2, that wouldn't give you 0. So I was thinking ahead to the signs here, which I didn't really need to be doing, but I was. So I wrote these signs down all. Okay? So don't do like I did. Make sure you understand. It's really easy to write something like that down and go on. Okay? Now, if you're working a problem, did all the steps right and made that mistake on it, well, I ding you. You know, you'd lose a third, maybe even a half your credit on the problem, but I'd give you a substantial amount of partial credit, depending on the complexity of the problem. So you'd have the final answer wrong, but the process would have been right. And I usually, depending on the situation, value the process over the final answer. Because open math values the final answer over the process. Okay? So I know that you're getting feedback on, this is right or this is wrong on your final answer. Okay. In open math, I'm a little more forgiving than that. And then a lot of times I'll see that you just left the I off of these, okay, in open math and got 0 points. I'd give you half credit. And then I'd write you a note. Says, hey, gotta include that I. And in my pre-calculus class where you're submitting copies, I'd look at what you did. Okay. And if what I'm saying is just fragments, and that's probably consistent with somebody who didn't bother to take the test. Okay, because they're not doing the work in a orderly, logical way that reinforces what they need to know when they come into the test. Okay. So anyhow, that's what you get. Now, two x minus 4 and 3x plus 5 are linear factors of P of x. X squared plus 4 is what we call an irreducible quadratic factor. Irreducible since there are no real zeros, okay? But we've seen that we can express this thing as linear factor, this is linear, and this is linear if we allow complex valued solutions. So if we allow complex valued solutions, including 4i and negative 4i. Okay. These don't give us x intercepts. I say they can, however, result in wiggles. They give us wiggles. So when we have a graph that in our analysis, our best guess maybe is it looks like this. If it has wiggles, we don't know where to put them. Okay, but it might come down here and have a little wiggle before it goes down here. That wiggle won't go through the x-axis, won't take it through the x-axis. But it's a result of those complex zeros, which do affect the real behavior. Okay. Now, that's a fairly deep idea. It's there just to give you full perspective. The bottom line that you really need to know is you can always get 4 factors. There are always 4 factors. You can't always find them all, but there are always 4 factors for a degree 4 polynomial. Some of them might be repeated, like we had x minus 3 or x plus x minus 3. X equals 3 was a repeated 0, okay, for the second polynomial, okay, that we looked at. You count the repetitions. You know, you get x equals 3 here, and you also get an x equals 3 from this. It does occur twice, and it does create that little parabolic 0 at x equals 3, the one we saw here. Okay. So you don't really need to totally understand that the complex zeros can give you wiggles. But if you're going to go on and take like an engineering calculus course or something that at that level, it's worth knowing that. So you have a deeper understanding when you start analyzing these things using derivatives and critical points and all that stuff. Okay. So I wanted to mention that. But if you didn't understand it, and if you don't care about it, okay, it's not going to affect you in this course. I'm never going to test you on whether the complex zeros can give you wiggles, but you do need to be able to find them. And that's one of your upcoming assignments. Okay, I want to play off of these 2 examples here a little bit more, because I want to do a rational function. So okay, and I want to put one of these over the other. I'm going to say 2x minus 4 in the numerator times 3x plus 5 times x squared plus 4 divided by x minus 3 times x squared minus 5x plus x. Okay. Now, the zeros of this numerator also make this 0. Okay. So So R of X is also 0. I could have said it X equals 2 and X equals -5/3, but that's implicit from the way I wrote it before. So R of X is also 0 at these two values. Okay. So if we're doing the graph, we can say, okay, now let's be sure. Okay, I'm safe doing this. That's X equals 2. X equals -5/3. You got these points. If X equals 0, Y equals R of 0, R evaluated at 0. We already evaluated the numerator and the denominator when X equals 0. We had -80 in the numerator, and in the denominator, we have -18. Now that reduces a little bit to 40/9, which is between 4 and 5. 4 times 9 is 36, 5 times 9 is 45, about halfway between 4 and 5, a little less than halfway. So I put X equals 2 here, and I didn't need to do that, but I'm going to need it anyway. So I can say that, okay, with this line, Y equals 40/9, which is 4 and 4/9. If you need to do anything else more with the Y scale, okay? So that makes sense? So the other thing is the denominator is 0. If X equals 3, and that has multiplicity 2, or X equals 2. Uh-oh. Well, that's a big problem. Okay. I wanted to address this, and it just bumped up. I'm a little careless with my zeros. The randomness, which wasn't all that random. The denominator is 0, at the same point with the numerator is 0. Okay? They share a 0, so they share a factor. Okay? Well, if we write this thing in completely factor form, we have a complete factorization. R of X equals 6 times the quantity X minus 2 times the quantity X plus 5/3 times x squared plus 4. And that's divided by x minus 3 times x minus 2 times x minus 3. Okay, why is a denominator like this? Because the highest power term is x cubed. It's got a 1 in front of it. So we don't need to add a number out here like we did here. But all I've done is I've used the zeros to get these factors, and I've used the zeros to get these factors. Since we have zeros of the denominator at x equals 3 and x equals 2, and 2 of them at x equals 3 and 1 at x equals 2, we can write this as x minus 3, that takes care of x equals 3, x minus 2, which takes care of x equals 2, and another x minus 3, which takes care of the second x equals 3. Now that we have this, the x minus 2 can divide the x minus 2, okay? This equals 6 times x plus 5/3 times x squared plus 4 over x minus 3 times x minus 3, which we could write as x minus 3 quantity squared. But x can't be equal to 2. Because if x is equal to 2, x minus 2 is equal to 0, and we can't divide by 0. Division by 0 is undefined. This means we have to exclude x minus 2, x equals 2 from the domain. So what we say is, no, darn, we don't have a 0 here. I have no good place to write it. No 0 here, and x equals 2 is excluded from the domain because x equals 2 makes the denominator 0. You can't have a 0 denominator, even if you can divide the thing out. You call that a removable singularity. You'll see that in open math. If not here in your calculus course. Okay. So this is what we've got so far. However, the zeros of the denominator, we still have a 0 at x, 0 of the denominator at x equals 3. So here we've got the line the denominator is 0. I don't have enough board to write what I want to write because I didn't anticipate that I did that one ahead thing. But it's okay because it's something you need to see. Just pondering how to handle board space here. And my solution is surprising. Shouldn't be surprised it took me that long to figure that out. But it did. Okay. Now, most of the things are halfway making sense. Okay. Our of x turns out to then equal 6 times x plus 5/3 times x squared plus 4 over x minus 3. And I'll just say x minus 3 squared. Well, this equals, and x not equal to 2. And this equals 6 times x plus 5/3 times x squared plus 4 multiplied by 1 over x minus 3 squared. Well, this is just the reciprocal squaring function that you know from chapter 1 that you should know. We haven't, in pre-calculus, in my section, we didn't go over how to construct this thing. It's pretty easy to construct. It'll probably have you construct it, sometime before the fun. But right now, what's the graph of this look like? Here's your toolkit 1 over x squared. Okay. So your toolkit 1 over x minus 3 squared is shifted 3 units to the right. This is the y-axis. So there has a line x equals 3 here. And we just shift the thing to the right. And that's a graph of one over x minus 3 quantity squared. Now, when x is 3, all this stuff is close to, what's that? That's about 13, and that's about 5. That's 65 times 6, about 330. Okay. All this other stuff is about 330. So you got to vertically stretch this thing by about 330. Okay, so it gets really big and really skinny. Okay. I don't absolutely have to know that. What you really want to take out, and the thing that'll pretty much satisfy me in my pre-calculus course, and hopefully in any other pre-calculus course, is you just know that the thing has to look kind of like this. It may be stretched and maybe inverted, because if this was negative, it would have to be upside down. Okay, and you should understand all that from chapter 1 if you don't go back and review that. Okay, that means that I have a vertical asymptote at x equals 3. Well, what's that look like? Vertical asymptote at x equals 3 looks like this. There's a temptation. It's hard to draw this like this curve to come back in a second. Kind of fill into that trap too, but it's got to do this. Okay. It's got to do this. It's got to be up this way and not down this way. It could be down here like this. But all this is positive when x equals 3. So you're multiplying the reciprocal squaring function, shift it over 3 units by positive numbers. Okay. So we've got that. We've got the y-intercept somewhere, I think. Yeah, here's the y-intercept. And you've got long run behavior. You got degree 4 divided by degree 3. Then the long run is a degree 1, which is linear. If you do a long division of this one into this one, you're going to get an x plus something over your division. what this means is your long run behavior is linear. Okay, so that means it goes this way and it goes this way. But this asymptote is twisted around a little bit. Okay, so it's pretty close to linear down here. And I've kind of distorted it. I don't have room to really draw it right, so I'm going to do it here. Okay. This drawing isn't quite working out. Simply because this thing is way too steep. So let me redraw what we get. And of course, open that. So it's coming down from here, coming down from here. I needed more vertical space because this curving of the asymptote curves much higher than what I was able to draw here. Okay, so we've also got this point, and it's like a linear function. We could do the long division of this denominator into this numerator. Just expand them both and do a long division. It'd be just kind of one step. It'd be a pretty simple long division. And we find that this is kind of like an x equals a y equals 6x function. Okay. A little more to it than that. But kind of does this. And it's kind of hard to draw this one accurately. It comes down here, goes through here, and then takes off like this. It gets pretty straight when you get down here. Up here, comes down like this, and it takes off like this. And it gets straight, same way this gets straight. And it actually becomes parallel to this. Now, I don't want to say too much more about that, but open math will show you what to do with that. Okay. That all involves stuff that you all have done pretty well in the homework. Okay. So that's an overall picture of the way you analyze a rational function. There are a lot more details, a lot more examples we could do if we had time. But yeah, do the stuff in open math. We'll see how you do on it. And then, you know, we can address it. Can you factor x squared plus 5x minus 6? Well, if you're good at factoring, you see that's x plus 6 times x minus 1. Okay. And that's one of the easier things to factor. If not, you solve x squared plus 5x minus 6 equals 0. And the quadratic formula very quickly gives you 1 or -6, that's right. Just making sure I wrote it down, right? Okay. It had to be 1 or -6 because this is how it factors. If you don't know that this is how it factors, this tells you this is how it factors. Well, if these are the zeros that you get here, then this has to equal this. Because this is what has those zeros. Okay? So if you got the zeros, you know how to write it. How you factor x squared plus 3x plus 10. You get x equals -3. It's all going to be over 2. You're going to have plus or minus what? It's going to be 9 minus 40 under the radical. Your zeros are then -3/2 plus square root of 31 over 2i. And -3/2 minus square root of 31 over 2 times I. Now, some people in my pre-calculus class went ahead and did the complex zeros homework. They didn't pick up on the fact that the assignment was delayed until Saturday because we didn't have class Tuesday. Okay. And so I got to see what they did. And when you do it, if you haven't already done it, some of you might have. A lot of people were getting these zeros, but forgetting to write the I when they put it into open math. Okay. And then I checked their homework that they submitted and they had the I in there. Well, I gave them half credit then. So now I'm going to charge you half credit for this because you really should have known to put the I in there, but you obviously did everything right. It even had it right on your written work. But you know, open math is one correct answers. Okay. So I'm going to take off half credit, but I'm giving you half credit. I didn't have, open math didn't give them any credit, so I gave them half credit. I didn't give them full credit, even though they almost deserved it. Because of, you know, let open math be pretty strict, but have a little mercy. Okay, so anyhow, there we got it. So what can we say? It's like we said that this was this times this. Is going to be x minus this root times x minus this root. Okay, x minus this one times x minus this one, because if x equals then this one, then this is going to give you 0, right? And if x equals this root, this is going to give you 0. You don't understand why? Go back this part right near the end of the video and write it out. Substitute x equals this, substitute x equals this, you'll find out that you get 0 either way. Okay? And that, of course, then equals x plus 3/2 minus square root of 31 over 2i. times x plus 3/2 plus the square root of 31 over 2i. So that the factored form of this polynomial ultimately we can fill in it's x plus 4 times 7x minus 9 times x minus x plus 1 I wrote the signs down wrong here. Should be x minus 1 here and x plus 6 here. Okay. And I'd only give myself 1/3 credit if I put that in. Okay. Okay, anyhow, it's x minus 1. X plus 6 times x plus 3/2 minus the square root of 31 halves I times x plus 3/2 plus square root of 31 over 2i parentheses. You can't read that last one, but it's the same as this one. There are your factors. This, and this come from this. This and this come from this. Okay. Now that's a completely factored polynomial. You see what your zeros are. They're complex. Two of them are complex in this case.